And
That's
today
great.
I will be presenting pseudo-marginal MCMC on symbolic data analysis. This work is ongoing and collaborated with my supervisors, Robert, Scott, and Matthias. To introduce what is symbolic data, you can think of symbolic data as like aggregated level data. So the classic statistical approach for computing likelihood is you assume independence between each observations, and then you take the product over one from I from 1 to n. So if you have 1,000,000 observations, so probably you will do 1,000,000 computations for the likelihood, and saying that you compute likelihood for each individual observation. So this work is based on the framework proposed by Boris' paper. And symbolic likelihood has the formula, the second last line here. So it's pretty complicated, but it uses some summary statistics. And you can think of n is the numbers of observation. SP is the numbers of the observations on the boundary. S min, S max is the marginal mean and max across all dimensions. And LSP is the usual likelihood for the observations on the boundary. So if I give you let me give you a demonstration of what the symbolic data in this paper means. So if you can think of the symbolic data as like a hyper rectangle. So we only know the marginal mean and max, and we know the location of the red points here. So, but we don't know the exact location of the blue points inside the rectangle. We only know how many blue points we observed inside the rectangle. So the key elements of doing analysis based on symbolic likelihood is we need to compute the likelihood function itself. It brings us two challenges. The first is the analytical solution of the integral is not always available. Even GX is like a simple distribution, say multivariate normal distribution. In high dimension, we can't get the analytical solution of the integral. The second thing is the variance of the log likelihood estimates increases quadratically with the numbers of the observations. Say if n is equals to 1,000,000, then if we estimate the log the likelihood, then the variance of the estimates will be increasing a lot by having n as a large number. So we propose two solutions here. The first is we use past sampler with Poisson estimate or an approximation method to get an unbiased estimate for the log likelihood estimates. The second thing is to control the variance of the log likelihood. We use the block pseudo-marginal MCMC to control the variance of the log likelihood estimate. So without telling you too much details, this is the application. We successfully applied this methodology to like 10-dimensional multivariate normal distribution with the data set size as 500,000. The result is like 4 or 5 times faster than the MCMC. Sorry, it's my the second result example is ongoing. So we are trying to fit the model for heteroscedasticity error structure. So data size is about 5 million. So it's like an ongoing process. And this is the reference. And thank you all for listening. Any questions?